nanohub.org.
Online simulation and more for nanotechnology.
So what I'm going to do today is I'm going to go through a quick reminder of what we talked about in the previous two lectures, and then we'll talk about the interpretation of probability as a representation of our state of knowledge, which is something a little bit different than what you should than what you are probably used to. We will talk about the common sense assumptions that a probability theory would like to satisfy, and how these assumptions lead almost uniquely to a set of probability rules. One of them we're going to call them the product rule, and the other one we're going to call it the obvious rule, because it's just obvious, okay? And then we'll introduce these two rules, the obvious rule and the product rule, and we'll show how everything that we would like to compute can actually be done just with these two rules. And we'll do a little bit of practice. Actually, we'll do as much practice as we can during the 1 hour we're going to devote on this. So even if I don't manage to finish all the things that I would ideally like to do, the handwritten notes will be online with all the examples completed, and you should really go through them before you start the homework. Otherwise, you may be a little bit on trouble. Okay? All right, so what we would do so far, we talked about the difference between statistics, machine learning, and assertive quantification. The difference is that we don't only care about data. We don't just make up the models. We rely on models that are coming from physics. Okay, so if you like, assertive quantification is statistics plus physics. All right, so we don't ignore the physics. The oldest example of UQ is statistical mechanics, and that modern UQ techniques are really not black boxes, but they do make use of the underlying physics. We talked about the distinction between aleatory and epistemic uncertainty. Aleatory uncertainty is uncertainty that cannot be reduced through randomness, if you like. Epistemic is uncertainty that you can reduce if you pay the price. And we also said that it's not really possible to distinguish between the two. There's not a clear-cut distinction. If you really push it hard, maybe everything is epistemic. Okay, but we also said that it doesn't really matter, because we're going to describe this uncertainty under the same framework using probability theory, and we're going to write statements like this: the probability of something being true given everything we know so far. And we gave this reference, and you should really go ahead and read the first chapter of this guy. Okay. Now, of course, just let me mention here that the uncertainty quantification we're going to talk about assumes that you already know that there is something about which you are uncertain, okay? If there are things that you don't know, we're kind of screwed, okay? We don't know what to do in that case. All right, so probability as a representation of our state of knowledge. And to motivate this way of thinking, I will talk about coin tossing. Okay, so if I ask you the question, you're about to toss a fair coin, like a quarter. Is it going to come heads or is it going to come tails? What is the probability of heads, let's say? What are you going to say? 1/2, okay? Doesn't make sense to choose anything else. We'll talk about it, why we pick 1/2, but the real question is, what do we mean with that probability, with the probability of heads? What do we mean by that? Some people say that the probability, they say, of heads is basically the observed frequency of getting heads if you do the experiment like 1 billion times, okay? The frequency, the observed frequency. You just measure how many heads you get, and you divide with the number of times you toss the coin, and that should converge to 1/2, okay? So, if you like, the probability is a physical property of the system. Now, I will argue that even in this simple example, the probability is not a physical property of the system, and you cannot interpret it as a frequency. We'll see how that argument goes. And the basic problem with the frequency interpretation is this: that a coin toss is not truly a random process. It is not random. It is very deterministic. How many of you have taken dynamics? Good. Okay. So I taught dynamics last semester, so I remember how to do the dynamics of the coin toss. Okay. So I'll show you with a simple example how this works. Okay. But before we do that, my interpretation is going to be the following. So we're going to call the probability of heads how much the guy who is arguing about the coin tossing problem, how sure am I that the coin toss experiment will result in heads? Okay? How sure am I about the result? This may have nothing to do with frequencies. It just describes my state of knowledge about it. And of course, if I assign this probability a 0, then I'm sure that I'm going to get tails. If I assign a 1, I'm sure I'm going to get heads. If I assign anything in between, I'm uncertain. And in particular, if I assign 0.5, it's like I'm saying, I don't really know what it's going to be. Okay? Now, if you haven't done so already, please watch this video where Percy Diaconis, one of the most important statisticians of our time, and most important Bayesian statisticians of our time, who's a professor at Stanford University, discusses how a coin toss is not really a random process. Okay? Now, we could analyze, if we wanted, a three-dimensional coin. It's fairly easy. Right? You need 12 parameters to do that. You need basically the positions and the momenta of 2 points on the coin, and with that information you can describe the dynamics of the coin, and you can write down the Newton-Euler equations and solve them. It's a dynamical system, and the only thing that is unknown is really the initial conditions. So the unknown thing for a 3D coin toss is the 12 initial conditions that you need to get started solving the Newton-Euler equations. But you can actually think a little bit, I mean, you can use the conservation of angular momentum, if you want, to throw the coin in any way you like, every single time, and make it look as if it is random. So, no matter how you throw the coin, the angular momentum is going to be conserved. So if you throw it in a way, for example, that the angular momentum makes an acute angle with the horizontal axis, then no matter how the coin, the coin moves, and it's going to move in complicated ways, its angular momentum will always point like that. It will go up, angular momentum pointing like that. It will come down, angular momentum pointing like that. And then you will just catch it with the face you threw it. And it would look as if it is doing crazy things. As soon as it doesn't bounce, okay? It should not bounce. So you can always throw it, let's say, with heads up. If the angular momentum angle is acute and you just catch it without any jumping around, you're gonna get heads every single time. So if you hear Diaconis talking about throwing the coin every time, getting whatever he wants, that's what he does. He makes sure that the angular momentum is at an acute angle with a horizontal plane. And you're welcome to go and do the analysis, but I'll do something simpler. I'll analyze the dynamics of a 2D coin. So this is the 2D coin. Let's say that the red, it's completely homogeneous, so the center of mass is right there, okay? And the red part of the coin, let's say it's the tails, and the blue part of the coin is the heads. And we'll just do a little bit of, so this should be in your notes, so you can go ahead and do a little bit of dynamics if you want. But this is dynamics that pretty much everyone should know. So you have your mass times acceleration of gravity right there. That's the only force that acts on the coin. You can select some variables to describe the position of the coin. Let's say that, we throw it from here. So we can use this variable y to describe how far up the coin has gone. And we can use this angle right there to talk about the angle that the coin makes with the horizontal axis. Okay, I'm gonna throw it, it's gonna go up, it's gonna satisfy Newton's laws, and it's gonna come down. Now if you remember your dynamics, Newton's law says that sigma of y is gonna be minus mg. Sigma of y is gonna be mass times y double dot, and sigma of y is minus mg, y double dot, and this gives us that y double dot is gonna be minus g. Alright, so this is one differential equation that gives us the position. If you remember the Euler equation, sum of the moments about, let's say the center of mass of the coin, taking counterclockwise as positive, is going to be moment of inertia about g times angular acceleration, theta double dot. But of course the moments about g are zero because there's basically only one force, and that force is the weight that goes through g. So we're going to get that theta double dot is zero. So here's your dynamical system that describes exactly what happens, okay? And you need to get it started. It's a dynamical system, second degree, 2 variables. You need 4 numbers to get it started, right? So you need y0, the position when you throw it, and let's say that you throw it from position 0. And you need the angle with which you start. Let's say that you start with a 0 angle. Just to simplify our analysis, these are parameters that you can pick. You know, the guy who throws the coin can pick these parameters. But let's allow you to throw it with a different velocity every single time. So the initial velocity with which you throw the coin is going to be up, right, positive, and v naught. And let's allow you to choose as well the angular velocity that you initially give to the coin. Now let's call that omega naught. All right, so now you have a dynamical system with 4 initial conditions, everything you need to solve this exactly. And you can actually solve it exactly. I'm not going to do this for you. I mean, I'm just, you just integrate y equals minus 1/2 gt squared plus at plus b, and you, find a and b so that the initial conditions are satisfied, right? Same thing for theta double dot is 0, and you're going to get this. Now, everybody should know how to do that, okay? So what is that? This is the solution of the Newton-Euler equations with the initial conditions that I assigned. And you have here the only thing that is unknown and may change what happens is that v naught, the initial velocity, and omega naught, the initial angular velocity. Okay, these are the 2 parameters that a guy who throws a 2-dimensional coin can pick. Okay, so using these parameters, of course, you can solve for the time it takes. You can solve for the time it takes to hit for the coin to hit your hand again. So you throw it, goes up, after time t1, it comes back to your hand, and you can solve for this time, and that time is going to be, I think, 2v naught divided by g. Okay, this is what it's going to be. So this is how much time it takes. Okay, and using that time and this equation star right here, you can find the angle that the coin will have when it hits your hand. Okay, and that angle is going to be 2v naught omega naught g. Completely deterministic if you know the initial conditions. It's ridiculously easy to solve it. Okay. All right, so depending on that angle, the coin will come up heads or tails, assuming, of course, that it doesn't bounce, okay? If it bounces, it becomes a little bit more complicated, but you could still work it out. All right, so you see that here's the angle that it should have if you want it to come out heads. Remember, heads is the blue, right? So if you want the blue up, so if the angle is within the following range, so theta t1 can be between 0 or pi over 2, or between 3 pi over 2 and 2 pi, then it will come up, it will come out heads. And if the angle is between pi over 2 and 3 pi over 2, let's go pi over 2 and 3 pi over 2, it will come up tails. It's that simple, okay? There's nothing random, really. Any questions? Where is the 1/2? Probability of 1/2? Nowhere, okay? We know exactly that it's going to come up heads or tails depending on the initial conditions. All right, so maybe it's sensitive in the initial conditions, and maybe if you cannot control them precisely, then maybe, maybe it will come up 1/2. I don't know, maybe it should be coming 0.51 heads. And that's actually what happens in a coin. And Professor Diaconis talks about that. but we'll see it in a while, all right? Anyway, so now you can define that variable that gives you either heads or tails. And you can say, depending on the initial conditions, I'm going to get tails if the angle is between this and that, and I'm going to get heads if the angle is between this and that, okay, or otherwise. So if you know the initial conditions exactly, there's nothing random. If you are uncertain about the initial conditions, then it is random, but it doesn't have to be 1/2, okay? All right, so let's spend a few minutes playing with this. So I have a hands-on exercise for you. Clone the notebook, okay, and start running it. And what you're gonna do is basically, I have written code that basically tells you whether the coin is heads or tails depending on the initial conditions, and all you have to do is play with the initial conditions a little bit to see that, you know, it can flip from heads to tails and so on. So let me give you about 10 minutes to finish that. So let's say 12:25 or so, we're going to stop it. Let me see you actually doing something and not sleeping, all right? So I know it's noon. Next time, bring your coffee. The day you will really need to know how to deal with a notebook is coming, and it's gonna be beginning of February, where you're gonna have a homework problem that uses the Jupyter Notebook. Okay, so hopefully by then we'll have everything fixed. All right. So I hope I demonstrated that it's not really a random process, the coin tossing, but that you know, if you cannot control the initial conditions very accurately, it's very sensitive to the initial conditions, right? So if you change omega naught a little bit, the result may flip from heads to tails and vice versa. Now you can actually study this a little bit more in depth, and this is where, you know, UQ differs from statistics. We're actually interested in what is the thing that is uncertain, okay? What are the physics, okay? So if you look at the function that gives you tails or heads given the initial conditions, you will see that, and you study, let's say, the points at which it changes from heads to tails, okay? So when does it change from heads to tails? Whenever the angle, the hit angle, let's call it, hits either one of these boundaries, like pi over 2 or 3 pi over 2. These are these curves, let's say, in the initial condition space at which you start the hitting angle hits the boundary, cause the coin to go from heads to tails. So if you look at that, if you draw these curves, the curves that at which the position of the coin is basically undefined in the initial condition space. So here you see I have V naught, the initial velocity of the coin, and omega naught, the initial angular velocity of the coin. And I'm asking the question, what are the regions of space, of the initial condition space, that are going to give me heads all the time and tails all the time? Okay, and these curves that I described before give you exactly these regions. So there's a region right here at the beginning that gives you always heads, okay, and then at that blue line, you're not really sure what's going to happen, but between the blue and the red line, you're going to get always tails, okay? Actually, let me do it here. So in this region, you get tails. In this region, you're going to get heads. In this region, you're going to get heads, 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 and then tails, 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 so on. So for example, right, if you manage to toss the coins for any initial condition in here, you'll get heads, no matter what, okay? Now what happens is that these initial conditions, these curves that define the boundaries of the head and the tail's initial conditions, they come closer and closer together as you go to high angular velocities. Okay. Now a person throws the coin somewhere around here at 2.5 meters per second. Okay, with an angular velocity that is between, let's say, 400 and 800. So there is a box of initial conditions that is common. And let's make it here. It doesn't really matter, okay? Let's say that this is where a person throws the coin. Okay? So all you have to do in order to find the probability of heads or tails is basically look at the area of this region and find how much area is occupied by the heads initial conditions. Okay? Now what happens is that as you go up, the area of heads relative to the area of that box is almost 0.5. Okay? That's what happens. But now, if you look at the actual way that a person throws a coin, which is around here, 2.5, and in this region, it's not 0.5. It's actually a little bit higher than 0.5. Okay? But not so dramatic. It is slightly more probable to get the phase with which you started. And by slightly, I mean like 0.51%, okay, instead of just 0.5. But of course, if you don't know how you started, it doesn't matter, okay? Then you can just say it's 0.5. All right? Any questions about any of that? So what I want to demonstrate that the probability should really be interpreted as our state of knowledge about the outcome of a random experiment, random in quotes, okay? And that most experiments are not really random, and we can actually say things about them, okay? And the whole point of uncertainty quantification is how do you take these physical statements and you turn them into numbers, probabilities, okay? Let's not do that because I suspect that we're not going to have time, okay? And let's move to the most boring part of the class, which is our probability background, okay? Most boring, but at the same time most important, because this is the only way that, we can guarantee that what I'm talking about, you actually understand what I'm talking about. All right, so let's see. Now, probability theory is nothing but common sense reduced to calculation. This is a statement by Pierre-Simon Laplace. It dates back to 1814, and Pierre-Simon Laplace is actually one of the first who interpreted probability in this way. So, Laplace needed probability theory to calibrate his astronomical models. Okay, he had observations of stars, of planets, had missing parameters, and he wanted to calibrate them, and he thought like that. I mean, he thought as his uncertainty about the parameters of his models being uncertainty about his state of knowledge and not true randomness. And he basically thought of probability as an extension of logic. This is very different than the view of probability that you guys may have seen in your probability theory course, where probability is all about sets and intersections and unions of sets and all that. So it can actually be much more general than that. It can be a tool that allows you to extend Aristotelian logic to uncertain logical propositions. And that's exactly what we're going to do right now. All right, so if you want to read about this, and you should probably do it, this is the number one reference, Probability Theory, the Logic of Science by Jaynes. Suggest you read chapter 1 and skim through chapter 2. Don't really pay too much attention on the derivations unless you really care about this stuff. But of course, keep in mind that we're going to be a little bit more moderate than Jaynes. Okay, Jaynes is of the opinion that everything that is not Bayesian is completely useless. That's very strong, Maybe true, okay? We're uncertain about it, but let's not be like that, okay? All right, so here's what we're gonna do. Let me introduce a few of our symbols. So A and B are going to be logical sentences. And by that I mean really any logical sentence whatsoever. So for example, it could be, A could be, I throw a coin and I get heads. B could be, I throw a coin and I get tails. Okay? I stands for information, is everything I know when I start arguing about things. Like for example, I know that the coin is a quarter and that it was minted with that particular metal, right? At that particular date, at that particular place, the time of the day, whatever, okay? Whatever may be relevant, okay? Whether or not I have Parkinson's that may affect how I throw it, and all that, okay? Now, the only restriction that we're gonna put is that A and B are not contradictions. It's not really the only restriction, but this is the only restriction I'm gonna tell you about, okay? So you cannot have a proposition that implies it's negative, right? You should not have a contradiction. It's as simple as that. Just leave it there. Now, a few symbols that I want to introduce. Instead of writing not A, I'm going to be writing this. Are you familiar with this symbol? If you're not, here it is. Become familiar, okay? You're going to see it. It just means not. All right? Then I will need also A and B. I will read this. A and B are true simultaneously, right? But instead of writing and, I will be writing A comma B. Okay? Or AB. And I will also need or. So A or B, I will be writing A plus B. Okay, you should read this as or. And I will talk about this again as we introduce it. All right, so here's our problem. Our problem is the following. Can we create a robot? And by a robot, I mean like a machine, a computer code that argues, that does logic, basically with uncertain propositions. Okay. So can we have an algorithm that can, let's say, argue about uncertain things? This is our problem. Now, if we created such an algorithm, what are the properties that we would like it to have? Okay? Of course, there is not a unique way to create such an algorithm. The first property that we're going to desire is that this algorithm assigns a unique number to each logical proposition, and that unique number, let's call it plausibility, but later on we'll call it probability, but let's just call it plausibility for now. And that number is a real number, okay? It's like 0.5, 0.6, 25, perhaps minus 13, okay? It's just a real number corresponding to the plausibility of a logical sentence, okay? That's all we say. So we could decide to build an algorithm that uses two numbers to describe the plausibility of logical sentences, or maybe 3 or 4, and create a different system. All right, but let's say 1 because it's the simplest. Okay, 1 number. Now this system should have qualitative. This is the first axiom that we would like to take. The second axiom is that the system should have qualitative correspondence to common sense. Okay, by that we mean that, if proposition A is true, if two propositions, let's say A and B are true, then the same number, whatever that number is, should be assigned to them. Okay? So you cannot take two propositions that are true and assign to one the number 13 and to the other one the number 15. You should assign to both of them the number 13. Of course, the right number is 1. Okay? But we'll look at that. We'll see that later. And so on and so forth. Okay? This is the qualitative correspondence to common sense. The other thing is that the system should be consistent in the sense that if you can argue the possibility of a logical sentence in two different ways, you should get the same answer. Okay? This is one thing. The system should use all the relevant evidence in its argument process. It should not selectively disregard some evidence because it doesn't like it. Okay? And you should also not use irrelevant things to come up with these numbers. All right. Anyway, now we'll see in a while. I will argue that these axioms, or desiderata if you like, result in a unique system for reasoning under uncertainty, which actually result in two possible systems. Okay, two possible systems. One of them is what we pick, and we call it probability theory. Okay, but there's another one that could also work, but it's a little bit strange. Okay. Anyway, so how are we going to talk about probabilities? This is an important slide. So we're going to argue about things like that. So we read the probability of a logical sentence A being true, given that we know that B, which is another logical sentence, is true, and all the other information that we have. So this vertical line right here is read conditional on or given. Okay, so let me repeat that. Probability of A being true, given B and I. I is everything we know. And if we understand that as, fixed on the background, you can ignore it, okay? You can just say the probability of A given B, but you should know that it's basically, everything is conditioned by whoever argues, okay? This is something that you must keep on the background. So any of these things is okay to say, okay? So you can say the probability of A being true, given that we know that B and I are true. The probability of A being true, given that we know that B is true, and understanding that I is on the background, or the probability of A given B. Okay? Obviously, this is what we're going to be saying, because everything else is just much lengthier. Okay? But this is what we mean. Any questions about this? Please practice with this, so that you get the true meaning of the symbols. All right. Now, how are we going to interpret it? So the probability of A given B and I is a number between 0 and 1. And if that number is 1, then we're absolutely sure that A is true if B is true and I is true. We're absolutely sure. Okay? This is as if saying B implies A. It's pure logic, okay? If probability of A given B and I is 0, then we're absolutely sure that A is false if B is true and I is true. So this is as if saying B implies not A. It's also pure logic. Now, any number between 0 and 1 is okay. And if that happens, if we get any number between 0 and 1, we're going to say that we're uncertain. And if we get 0.5, we're maximally uncertain. Okay? Am I going too slowly? It's kind of obvious, right? But I think it's extremely important that we actually, we speak about these issues and we speak about the language. Otherwise, I'm not going to be sure that you actually understand what I'm talking about. Okay? Now, there's this paper by Cox. Cox's paper is much earlier, it's like 1950s. This is the most readable version, modern version that I was able to find. That basically proves that if you want to build a system that satisfies these axioms, there are actually just two choices, and one of them is probability theory. Okay? And that system, in addition to these axioms, it should also satisfy two other rules. One of them I call it the obvious rule, and the other one I call it the product rule. okay, or Bayes' rule. But let's look at the obvious rule first. The obvious rule says that only A or not A is true, okay? Because it says that the probability of A plus the probability of not A should be 1. Big deal, okay? Of course, the only important thing here is that A should not be a contradiction. That's the only important thing. All right, but this is extremely important to remember, of course. If you are familiar with the set version of probability, that would be the probability of A plus the probability of the complement of A is 1. Okay, but this is much more general. And the product rule says that it's a little bit more, it's stranger to understand. This is straightforward to understand, but this is strange. It says that the probability of A and B is the same as the probability of A given B times the probability of B. This is very difficult to understand. I don't think that you can understand it for logical propositions. You can understand it for sets, and I will show you how it looks like for sets. And that's a good way to build your intuition. But you should write it with huge letters on a piece of paper and put it on your wall, because I'm going to use it about 200 times until the end of the class. This formula. Okay, not today's class, but in general, for the whole semester, okay? It's absolutely crucial. I mean, this is how you calibrate missing parameters in your models, for example. This is how you train probabilistic models. This is how you infer, you talk about, you get new evidence and talk about how this evidence affected whatever you're arguing about. So this is behind everything. Now, you might see it as Bayes' theorem, but it's not really a theorem. I mean, in the classical view of probability theory, which is the Kolmogorov view, it's actually just taken as an axiom. It is defined. The condition of probability is defined to be something. Okay? Now, in our version of probability theory, it is derived from the axiom. Uniquely. So that plausibility function should satisfy it. Anyway, let's try to understand it using sets. Alright, so I have here what is known as a Venn diagram. It's good to use Venn diagrams to understand these formulas, but you should not, but the formulas are actually more general than the Venn diagrams. Okay? But let's see how this works. So you have your prior information, you can visualize it as a set. So it's everything you know. And let's say that A and B basically specify a subset of that sample space. I mean, you have to talk about sample spaces. So this is A and this is B. Okay? What is the region here? This region is A and B. Okay, so these are the points that satisfy both A and B simultaneously. Okay? So now if I ask you, what is the probability? What do I have here? A given B. What is the probability of A given BI? What is that probability? Well, that probability, if I would like to visualize it as a Venn diagram, is this area divided by the area of B. So it's the relative area of the intersection of A and B. Okay, normalized with B. So look at that. It's probability of AB given I. It's this area right here. Okay? Divided by the area of B given I. That makes sense. That makes sense. Okay? Doesn't it? Kind of makes sense. So this is how, in traditional probability theory, this is how Bayes' rule is defined. You just look at the Venn diagram and you say, okay, here it is kind of obvious, it should hold. Okay, let me just define it like that. Okay, in our version of probability, it is more fundamental than this. But you can, of course, just understand it like that. Okay, then if you rearrange it, you can write it like that. PA given BI times PBI. Okay, if you rearrange. Any questions? Okay, I'll accelerate. very important thing, there's one thing that I want you to understand. These two rules, the obvious rule and the product rule, are all we need to compute any probability we like. This may seem ridiculously general, but it's true. There's nothing else. Okay, but it's as if I'm telling you we're doing dynamics and I tell you, you know what, it's all Newton's law. Sigma F equals m times A, that's it. There's nothing else. There's really nothing else. Okay, but there are some tricks that you need to know about how to apply these rules. Okay, so these are our Newton's laws, if you like. Okay, so it's extremely important to remember these. All right, so let's practice a little bit with them. Let's do a very simple example. We have a box with 10 balls in it. How many are red? 6 of them are red and 4 of them are blue. Here they are. And now what we do is we close the box and we give it to somebody else and we tell them shake it. Okay? Shake it as much as you want. Go away. I don't even want to see you shaking it. Okay? And then we tell them come back in the room. Let me just pick one. Okay? Let me pick one. You have to do that. Otherwise it's not really random. Okay? So let's start computing a few probabilities. So let's say that, let's call A the sentence, the first ball we draw is blue. Okay? That's our sentence. So now we're going to come up with a probability. Now, please pay attention. The two rules, even though you could use them to compute everything, really, they're not sufficient to compute your starting point. So what is the probability of A given I is not specified by these rules. We need other principles for that. And then we're going to devote a whole lecture on how to come up with a good answer for this. Of course, here the answer is obvious. You have 10 balls, 4 of them are red, so the probability of getting a red one is 4 divided by 10. Okay? Now, we argue like that, and it may seem like this is undisputable, but it's actually also an axiom. Okay? And we'll talk about the axiom that we are using right now. We're going to talk about this explicitly on lecture 5. Okay? The axiom is called principle of insufficient reason. Okay? We'll talk about that. But anyway, it kind of seems obvious. Let's get started with that. All right, so in the same manner, what is the probability that we get? Actually, what did I do here? 4 of them are blue. Okay, so 4 over 10. What is the probability that we get a red ball? So in your notes, in your handout, there's a typo, okay, which I have fixed here. So it's going to be 6 divided by 10. And there's 6 red balls out of 10. Let's see if, we can compute it in one more way. Let's see if we're going to get the same answer. We can use the obvious rule to write this, right? And this is 1 minus 4 divided by 10, and we're going to get 6 over 10. So our system is consistent. We compute it in 2 different ways. We get the same answer. That's good. Okay, but of course this is ridiculously easy, okay? Let's do something that is a little bit more difficult. So now we have the sentence A, the first ball we draw is blue, and B, the second ball we draw is red. Okay, so A, we draw first a blue one, B, we draw the second one, and it is red. And we want this probability, which we read the probability that we draw red on the second draw, given that we have drawn a blue on the first one, given everything else we know about the urn. Okay, so how can we argue about that? This is also something that the axioms are not enough to give us, and we have to do it with the principle of sufficient reason. So we say, okay, so you're telling me that you have already drawn a blue one, all right, so now instead of 10 balls, you have 9, okay? And out of the 4 blue ones, you took 1, but you didn't take any reds, so there's still 6 reds in the urn, in the box. So the probability is 6 over 9, okay? Again, principle of insufficient reason, you just think about it and you come up with it. It's your starting point. All right, but now let's use this to calculate something more complicated. So let's find out the probability that we draw first a blue one and then a red one. How do we do, this is this probability. Probability that first A and then B. First a red one and then a blue one. Actually, first a blue one and then a red one. I confused myself. All right, how do we do that? Well, now this is the point where we can use the product rule and express this probability in terms of probabilities that we already know. Okay, so we're going to do the probability of A given Bi times the probability B given I. Is this good enough? So we have found that, okay, the probability of A given Bi, we have found that. What about this one? We don't seem to have this one. Actually, we don't even have the first one. So even though, this is still a valid thing to write, we don't really know these probabilities. So we should not be afraid. We can delete it and do it the other way. We can say probability of B given AI times the probability of A given I. You can interchange A and B any way you like. The product rule is going to be the same, okay? If you just change the labels of the sentences. So this thing holds here, and we know both these probabilities. Now this is the first one. This one is the probability that we draw a red ball after we have drawn a blue ball, and this is the probability that we draw a blue ball in the first draw, okay? So this is going to be 6 over 9 times 4 over 10. Okay, whatever we get by that. Any questions about this? Okay. And you can do more complicated things. You can do the probability of not A and B, which means instead of drawing a blue ball, you don't draw a blue ball, you draw a red ball. So this is the probability of drawing 2 red balls in a row. What is that probability? Okay? And you can work it out in the same thing. Be my guest and do it on your own time. I'm going to post whatever the answer is later. Okay? Any questions about the application of the rules? Now, these rules are sufficient to get whatever you want. Another a theorem, if you like, that you can prove with these rules is this right here. The probability of A and B is the probability of A plus the probability of B minus the probability of both of them being true at the same time. Okay? Again, this is easy to understand if you look at the Venn diagram. Okay? You're looking at the probability of A or B, so you're looking at basically this area. All right, this is the area that you want to compute. So if you take the probability of A and the probability of B and you add them together, you double count this area right here, which is the intersection. Right? So you need to subtract it. And that's how you can understand intuitively this formula. And of course, this is one of the formulas that you kind of have to remember. Okay. Questions? All right. I was planning to prove it, but instead of proving it, I'll just show you the proof. Okay, so even though you can understand it intuitively, you can actually derive this formula by just applying the obvious rule and the product rule repeatedly. And it's a good exercise to actually try to do it on your own. It's not that trivial. It's just 2 things that you should just repeatedly do. It's not difficult, but it's not trivial. It takes I couldn't do it in less than 4 lines, for example. Okay? But it's possible. Actually, it is possible to derive anything you want with just these 2 rules. So this is a good thing to practice with. So I'm not going to post them. I'm going to give you like a day or so to practice with it, and then I'll post it. All right, now I would like to also talk about another important rule, which is called the sum rule of probability theory. Now, it turns out that the product rule with the sum rule are basically the most useful two formulas that you should remember. Okay, so the sum rule says that pick any logical sentence you want, anything you want, okay, and then pick a series of logical sentences, B1, B2 up to Bn. Okay, finite, but pick a finite number, because if we pick an infinite number, then we have to do math. Okay, so just pick a finite number. Make it a billion, okay? But let's make it finite. And these logical sentences are such that only, definitely one of them is true. Okay, one of them has to be true. At least one of them has to be true. Okay. But they're mutually exclusive. They cannot be true. No two of them can be true at the same time, right? So this sentence here, this statement there says, well, one of them has to be true because probability of B1 or Bn is 1, so one of them has to be true. And this one tells you that if you take any two of them and you ask the question, what is the probability that I and J are simultaneously true, you get 0. This cannot happen. Okay? So you say then that they are mutually exclusive. Now the sum rule states that if you pick sentences like that, then you can take this probability, the probability that A is true, okay, where A is an arbitrary logical sentence, and decompose it to simpler probabilities like this. Like probability of A and BI being true, sum over all the possible I's. Okay? So basically it tells you take any sentence you want and any sequence of mutually exclusive logical sentences, one of it has to be true. And using that we can take a complicated probability and break it down into simpler ones. Okay, that's what it tells you. We'll see examples of this later on, for sure. And then if you use the product rule, right here I'm just using the product rule for each one of the summands, and you can just expand it like that. Okay? Let's understand how it works. So here you see I, the information I have, and then I have decomposed I in 4 areas, B1, B2, B3, B4. Now look at one of these B's have to be true, assuming that this area here is negligible, of course, okay? I just wanted to be able to show you I on the background. So one of the BI's has to be true, so they satisfy this, the first, let's say, assumption, and no two of them can simultaneously be true because they don't intersect each other. Okay, so you see that they don't intersect each other at all. All right. Now you take an arbitrary proposition A and you put it in the space of I's, if you like. All right. And you can compute its area basically, right? So this is the area that you want to compute, the area of A. And you say, I'm going to compute the area of A by summing up this area, this area, this area, and that area. What are these areas? Well, this is A intersected with B1, A intersected with B2, A intersected with B3, and A intersected with B4. So you can express the probability of A by breaking it down to smaller, simpler probabilities like that. Okay? So this is another device that you can use to understand the Venn diagram. You can use it to understand this formula, the sum rule. Okay? But again, you should remember that the sum rule is more general than just areas or sets. It's much more general. Okay. And you can prove it by just using the product rule and the obvious rule. You don't need anything else to do it. Of course, you also need induction. So you say, I'm going to prove it for B1 and B2, and then I'm going to assume that it holds for n, and then you can show that it also holds for n plus 1, therefore it holds for any n. Okay, so how would you do that? You would start by this, B1 plus B2, given I. All right, this is an identity. If this probability and that probability, they should be exactly the same because this is definitely true. So it shouldn't really affect anything. And you can just move on from that. And I will post this. Okay, but try to do it on your own. Try to just derive it with the product rule and the obvious rule. It should take like 2 or 3 lines, this one. All right, so let's get back now to our box experiment and use the sum rule in one question. So I remind you that you have a box and you have 4 blue balls and 6 red balls. A is the sentence, the first ball we draw is blue. B is the sentence, the second ball we draw is red. Now I can understand that it's next to impossible to follow a guy talking about probabilities, about balls from boxes, what is red, what is blue. I can understand that. I mean, it's totally natural, okay? Nobody can do it. I don't think I can do it. But what does that mean? That means that the only way to really understand what I'm talking about is for you to do it on your own time, to meditate with it, to think about the box, to count the balls, to do it again. That's the only way to really understand it, all right? So don't expect to really get it here because it's just confusing to talk about balls, okay? Anyway, let me just show you now how I can compute this probability. The probability that the second ball I draw is red, and how I can decompose that. So I can decompose that by introducing 2 mutually exclusive sentences, one of which is true. So one of them is A, which is the probability that the first draw gives me a blue ball, and not A, which is a sentence that tells you the first draw is a red ball. So we're basically going to decompose what happens at the second draw by talking about what happens in the first draw. So we say the second draw, we want the second ball to be red, and we're going to say, okay, the second ball is red, good. So the second ball is red. What about the second ball being red and the first ball being blue, plus the second ball being red and the first ball being not A, that is red, okay? So this is the sum rule. Meditate with it at home because there's no time, okay? I read it again. I take the probability of the ball being red at the second draw and I decompose it based on what happened in the first draw. Okay, so I say in the first draw, I could get a blue or I could get a red, and that's all I can get. Therefore, I can decompose what happens in the second draw based on what happened in the first draw. Okay, and then each one of these, I can actually calculate it with the product rule and get a definite result. So I'm going to pause this, study it. So I'm sorry, I can see it in your eyes, okay? That you're either tired or bored, or this is very obvious to you, or you don't get anything. One of these mutually exclusive things is going on, okay? And that's totally fine, all right? But that's what's going to happen if we try to do half a semester worth of probability theory in 1 hour, okay? So that's totally okay. You're going to have to go and study this on your own, all right? Don't worry about it. Now I'll show you, I have 4 minutes, I'll talk about this example and I'll give you the solution online. And this example is on your homework as well, okay? So you better study it. So here's how it goes. We're studying a tuberculosis test. We want to decide if it is effective or not, okay? And we have the following information. We have done experiments and we have gathered this information. So first, the percentage of the population that has tuberculosis is 0.4%. Okay, 0.4%. This is something that we can just measure, okay? And then we run an experiment with our tuberculosis test, and the experiment has revealed these things. If a tested patient has the disease, then 80% of the time the test comes positive. And this seems like a pretty good test. So if you have the disease and you do the test, 80% of the time, it will say that you have it, okay? 20% of the time, it's gonna be a false positive, all right? This is the first thing that we measure. The second thing that we measure is that if a patient does not have the disease, 90% of the time, the test will come up negative. So in other words, the probability of a false positive is 10%, okay? So I repeat, 80% of the time, if you have the disease, it will tell you that you have the disease. 90% of the time, if you don't have the disease, it will tell you that you don't have it. Now, my question to you is, do you think that this is a good test? Would you do it? And this, I want to see who thinks that, yeah, sure, it's a good test. Who believes that it's a good test? Remember, 80% and 90% prediction accuracy. So who thinks it's a good test? Seems pretty decent. Seems okay, right? Who thinks that it's actually a ridiculous test? Have you seen it? Have you worked it out? Why do you think it's a ridiculous test?
Because 10% of the people that don't have it are going to be told that you have it, and most of the people don't have it. So a ton of people in the whole sample space are told they have it.
Exactly. But you argue like that because you are actually using inside your brain Bayes' rule, or you have a lot of experience with such tests. But arguably most of us do not really, I mean, we think that it's a pretty good test, and we'll probably pay good money to take it. I wouldn't do it, actually, to tell you the truth. I would first argue about this, all right? But you know, maybe when I was in high school, I would do it, okay? But the right answer, is this, right? That it's actually a ridiculous test. But the safe answer is I don't know. Let me think about it, okay? And then decide. So if you think about it, and this is what I have, this is in your handout, and you can work it out. And I guide you on how to calculate the probability that you have tuberculosis if the test is positive. All right, so we can work out this probability. What is the probability that the test is positive, that you have tuberculosis if the test is positive? Because this is basically what a doctor should use to decide, what happens with you. You know how much this is? Do you think it's greater than 0.5? Who thinks it's greater than 0.5? It's actually 0.03. Okay? So even though the test tells you, if you have tuberculosis, 80% of the time it will tell you have tuberculosis. If you don't have tuberculosis, 90% of the time it will tell you don't have tuberculosis. But if you ask the question, what is the probability that I have tuberculosis given that it is positive? The answer is 0.03 because the base rate, the percentage of the population that has tuberculosis is extremely low, so it's unlikely to have tuberculosis in the first place. Okay? You would be amazed on how many medical tests are just like that. And we're actually looking at the likelihoods instead at the posterior probabilities. Okay? So you'll have the chance to play with this in your homework. And I will post basically the solution to all these issues, these slides by tomorrow, so that I can give you some time to work on them. All right?